Hello everyone. So finally I'm back with another video. Now we want to continue with our building GPT-2 series and we have wrapped up last time by implementing models like LSTMs, recurrent neural networks, GPT from scratch. Uh, Now is the time for GPT-2 to start building it. So um, So basically, we'll break this up break this video of building GPT-2 into multiple parts. First part would be of building a skeleton class, how a GPT-2 model would look like, and loading weights from Hugging Face, and trying to inferring using forward method with a custom class. So let's start with it. So this is the paper, Language Models are Unsupervised Multitask Learners, that introduced GPT-2 model in 2019. It was basically a scaled up version of GPT model, which is a decoder only model. So this paper is attention is all you need. So the decoder part, the right part of the network becomes the GPT basically. And GPT-2 is a modified version of this, which you can think of it as something like this. If you compare these two, what you notice is mostly it is same. In The inputs are similar, positional encoding and output embeddings get added together to go into the transformer blocks. There would be n transformer blocks. Each block will have each block will have multiple components like mask, multi-head attention, feed-forward network, and so on. And then after n layers of n blocks of these self-attention and feed-forward, we'll have a linear transformation and a softmax for calculating probabilities across the vocabulary. One thing you'll see difference here is whenever the residual connections are happening across feed-forward or multi-head attention, there's add and norm here in the old method of attention is all you need paper. But in the new methods now, the layer norm, the norm part of it is getting calculated before the input goes into that particular module, and the add happens as it used to be. So this is basically residual connection. The input gets layer normalized and then feeds into the module, and then it adds into the residual connection. So this is one of the minor differences that exist now. So now almost all of the LLMs that you'll see will have layer norm before the module. Um, and So this model was released in multiple sizes, 117 million. So let me, instead of this, I'll, let's take a look at the model card here. So this is the official GPT-2 repo by OpenAI. And the model card here has the details. So there were multiple versions released. 125 million was the smallest model, 355, 774 million, and 1.5 billion parameters. So GPT-2 is basically a 124 million parameter that we are going to build from scratch now. This was written and developed in TensorFlow. Therefore, the weights we cannot take the weights from them directly, and what we are going to do is the Hugging Face community has translated it into PyTorch weights, and we can use these models to uh, import from tools for initial purposes. All right, so a good place to start would be um to basically look at how the GPT-2 model looks like, the architecture of it from Hugging Face to start with. We'll import GPT-2 LM head model uh, from this transformers library by Hugging Face, and we'll see how it works. Basically we can initialize a model with GPT-2 dot this API from pre-trained API and pass in the model name, which is GPT-2. So there could be multiple different model names. There could be GPT-2 medium, there would be GPT-2 large, there would be GPT-2 XL. So XL is the 1.5 billion model. This is 755 something million model. This is 355 million model. So we are going to look at the GPT-2 model, and to do so, what we have to do is we have to look at uh, the weights and the layer names of it. So to do that, we'll need to look into something called a state dict of it. A state dict of this model is, it looks something like, sorry, so it looks something like this. There's an order dict object where you'll have different weights, their tensors, then next layer weight and their tensor, weight names and their tensor basically. So if we uh, get into these for key and value in this items, let's try to print um, key has, or we can just directly say v dot shape. Printing tensors for each would not be sensible, so let's print. So yeah, now we are printing the weights, the name of those layers, their sizes here. That's what we see, right? So WTE is basically token embedding, where you see this, if you see this, right? Input embedding. So this is what input embedding is denoted by WTE here. WPE is positional embeddings. So 1024, so basically this 50,257 by 768. So 50,257 is the vocab size, and 768 is number of dimensions for each representations we are going to use with this smaller GPT-2 model. And then WPE is position embedding. So 1024 by 768, because each positions is embedded into 768 dimension vectors, but there are 1024 positions. So when we were working on GPT model training, we were working with 8 block size. Here the block size is 1024, so the model can get input size of a number of tokens ranging from 0 till 1024. And then we see these ln1 attention. So h transformer dot h is basically, I think, is hidden. It means hidden layers. Hidden layers is basically a block here. So that's why h dot 0 is 0th block. It will have multiple components. Then h dot 1, it will have multiple components, and these all these components are repeated. So if you see here, h dot 0, it goes on till h dot 11. That means there are total 12, 0 till 11. There's total 11, 12 such blocks which come under h. Uh, then each block has multiple components. There's a ln1, which is layer norm, which is so each block has a layer norm. Then each block, then that block has a uh, attention weights and biases, projection weights and biases. So this is basically attention weights and biases. This is projection weights and this is projection weights and biases. These two things, linear and attention, include combine to make attention module, self attention module, multi-head self attention module. Then it would be again a layer norm, which is this ln2. Then there would be a mlp.cfc and cproj. So there will be a metal layer perceptron. There would be a two set of hidden layers here, CFC and CProj. So we'll look into it when we'll develop. But after this, then our one block has ended. Then we will repeat these blocks h.0, h.1, and so on. So basically, right now, first step would be to um, a first step would be to develop a class structure, a model which has a class which can look exactly like this with these names, with these weights, so that we can import the weights from Hugging Face's GPT-2 model, and then we can infer from it. So let's start. Uh, Before we do that, let's also try to uh, infer from this Hugging Face model once. So we are using TikToken library. TikToken library is a tokenizer library from OpenAI. This is very similar to what something like transformers import GPT-2 uh, GPT-2 tokenizer would do. So these both these libraries would give the same token outputs if we feed in a text to these. So they are almost similar. TikToken dot get encoding. We'll initialize a tokenizer. Let's say this is a prompt. So if we do enc dot encode prompt, what does it give? It gives us a list of integers, right? And this is basically a list. So what we can do is mm, consists this model dot generate something like tokens. I think with this Hugging Face model, it would be easier to use encodings from this because it comes out in a different format. Let's look at it for generation. So uh, it says stock dot. So you see both these outputs are same. Use either tick token or the GPT-2 tokenizer from Hugging Face. Uh, Now what we have to do is, okay, so this is how it will work. We encode the prompt with tokenizer.encode and return a PyTorch tensor. So here's the tensor that we got back. This would be our input IDs. We'll feed input. We'll feed these input IDs. Sorry. into output IDs to do the further generation. Let's say we generate 30 new tokens. So it would, but the generation would be still output IDs. Let me print the output IDs here as well. So these are the new IDs. So they will append on top of these existing IDs the new additional generations from here on. So we'll see how to uh, decode this. So tokenizer.decode, we can pass it to, see what it is. Mm, this should, cool. Yeah, so this should generate like this. I'm not a language, I'm a language model, not a language, I'm not a language model. So it is doing gibberish, but yeah, it is doing something. If we want to do something like so there's obviously a pipeline API from Hugging Face which makes all these multiple individual steps in a one-line code. But just to show you how it works, basically tokenizing the text into these tokens, then generating new tokens, predicting new tokens using the model, and then uh, decoding those tokens into the text that we have. This was our input, and this is the output that it has generated. So maybe it doesn't looking good. If you want, we can see with a different model. How does it look like? A medium model. Let's hide this for now. So next up, we want to write a class of model which give us a skeleton same as this. So we want all the named layers with these names and of these sizes for the smallest GPT-2. So let's start doing that. So I'll just import the prerequisites. All right, so first thing we need to do is we need to have a way of setting all these hyperparameters. So basically we can define a class, config class for it. So I'll say it as GPT config, and so we can define it as data class with this decorator. So what happens with this decorator is when you write any class under this decorator, it is not going to require some basic um, dunder functions for it, like basic initialization. So initialization can be done without writing any init method. So for example, if I write something like cap size and equals to 50,000 to 57, then we'll have block size. So block size, hello, then we will need embedding dimensions. We'll call it as an embed. This should also be an embed. So 768. Then we'll need an layer and okay, I think this does not need the comma here. And number of head is also is equal to 10. So this is the basic config that we'll need for um, the smallest GPT-2 model. So using this we can then write our model basically. So let's start with model now. So we'll name our class as GPT2, and this would be instance of nn.module. This taken input as a config. So here what do we need is um, initialize. We'll need self dot. You see, we'll need few things. Our parent name of all the modules is transformer, which would be a and it would be a uh, basically a named access named keyword names of these things inside, so we can initialize it as module dict. So we need to define each dictionaries here. WTE equals to heading fig dot config dot and embed. WPE is equal to and then dot embedding of config dot. Okay, so first let's do with only this much, and um, let's say we initialize the config GPT2 config, and we call a model is equal to GPT2 and pass in this config for kv in model dot. Let's look at let's see if we are going and we are at least able to get these names in this format or not. Yeah. Um, cool. So yeah, we are able to get the weights of the same names. See, WTE dot weight. We make a parent attribute transformer, which is a module dict kind of object, and inside this module dict we just keep pushing in all the layers. This is token embeddings, position embeddings under this dictionary object. Cool. So we'll just keep stacking things here. So after these WTE, WPE, then we have a H. So H is basically multiple layers, H dot 0, H dot 1 h dot 2 and so on. So this is basically we can think of it as a list of different layers wherein you have block of config for so something of this sort. We'll need to define this block, but yeah, block is not defined. That's okay. So basically this, or maybe we don't need to do it like this. We just need to, with module list, initialize. I need to give a modules inside. Mm. So for module list type object, we need a iterable, basically a list as input should be fine. So I have made it this as list. I think it should work without these square brackets as well. Still, let's continue. So all these h dot 0, h dot 1, etc. h dot 0, h dot 1 will come from this list of modules. Then after this, what do we have is, once we have all of these h's, all of the hidden or modules are done, then in the end we'll have layer norm to end with. So basically this is the layer norm, which I'll just show you that figure once more. Hmm. Yeah, so this we have put in initialize this token embedding, position embedding. Then we have initialized a list of these blocks as much as number of layer we want. Then after this comes a layer norm and a linear layer. So that's what would be lnf, which should be n dot layer norm, and this would be config dot embed. Then we would have, so then we have a linear layer. So I think, but linear layer, for linear layer we need, this doesn't belong to transformer dot ln transformer list. So separately we'll need dot lm underscore head, and this should be a linear layer because this is a linear transformation from this would be a linear transformation from config dot embed to config dot vocab size. Cool. So this is what we have now, right? Let's say if we don't put this for now, except all the h's transformer dot h in our network layers, we should get everything else otherwise. Yeah, so we are getting token embedding, position embedding, the layer norm after blocks, layer norms bias, we're getting weight and bias for these both, and then we get lm head dot bias. Okay, weight and bias. So I think we need to say here that bias equals to false. I think that comes from the GPT-2 paper. We'll take a look at it. That section where all the modifications are done. So now this looks identical except the h's. So for h, we need to define h. That's why I commented it out, because it won't run then. So let's get to defining this blocks now. So this block basically would be something like this figure, right box of this. So each block will have a multi-head attention, uh, proceeded and succeeded with some linear layers. Then this will basically a projection. Then it will have with residual connections done, and it will then be followed by a feed forward connection. So let's write block now. So here with each of the, okay, let me extract away one set of h's information so that it would be easier to look then. Cool. So here we'll have first a layer norm, then we'll have a attention layer, attention block. Inside the block particularly, we'll have a attention section, then we'll have another layer norm, then we'll have a MLP, which is basically a fully feed forward connection. So we'll have ln1 self dot attention to MLP. So layer norms would basically be n dot. This should be same for both layer norms. Now for attention, um, basically what we need is this attention would be a different class we'll have to define, because to compute this attention we'll need um, a lot of different things going on in between. So after this layer norm, which is ln1, we'll do this all these computations in a different object. So we'll call it as causal self attention, and we'll just pass config to it. And similarly, we'll do a different object for MLP, which would be a feed forward connection. MLP, pass this to it. Once we have this, let's quickly write the MLP class. So now again we'll need to look at the output. Yeah. So for MLP there are two different things. There is a CFC and there is a C projection. So basically this is a fully connected layer, and this is a projection layer. So let's take a look at the paper, what it says very fast. So I'm referring to again this GPT-2 paper doesn't talk much about the feed forward connection part of the transformer block here, specifically as far as I think. So it's more or less model related details are very much similar to GPT-1. Therefore, let me see what was the GPT-1 paper. Language model understanding. Okay, so this was the GPT-1 paper. So one difference it has from the attention is all you need is paper is it uses GALU non-linearity between the feed forward connections that we are going to write, whereas in attention is all you need paper it used to be the ReLU non-linearity, and yeah, there would be two linear layers, and there would be a ReLU or GALU sandwich between them. So we can uh, get back to writing, I think, the code. So this would be an n dot linear layer config dot and embed by. There's a 4 times multiplier of config dot and embed. And it will, in between these two there would be uh, the non-linearity, which is n dot GALU approximation equals to 10h. So there are two ways of calculating GALU non-linearity. GALU non-linearity is more or less it improves upon the discontinuity in the ReLU function that occurs at point 0. So there's no, it's not differentiable at 0 basically. So GALU or leaky ReLU, these kind of nonlinearities, they make it differentiable at that point, so it doesn't behave weirdly. So yeah, then we have these two layers. Forward of this would look something like CFC X self to self dot GALU X. Cool. So yeah, this should be our MLP class. Then let's write our so we have written MLP. Now we have to write causal attention class. Causal self-attention. Okay, so causal self-attention, if you it's almost same as the self-attention and multi-head self-attention that we wrote in GPT coding video, but there would be a slight difference in the way we are going to implement it. So can I somehow open it? Or let me bring in that code and paste somewhere here. Okay, so this is how the code was, the code that we wrote in our GPT implementation. So we were doing it in two different pieces. First, we are computing a single head of self-attention, and then we are using that head to do multi-head self-attention for um, let's say four different heads parallelly, and then concatenate their outputs. So here in single head, what we were doing is we were initializing key query value these matrices separately and in linear layers. Then we would in forward part of it we would do the projection of x on these kqv, which will get kqv. Then we'll calculate weights, which is basically attention scores between token and all the surrounding tokens. We mask it for masking the future tokens. We don't want to look at the future tokens. We were computing softmax, so that obviously masking and softmax both combined to complete the masking part where future tokens don't get any attention scores, and then we do drop out. uh, and what we do is we then we are matrix multiply our attention scores with the value, which is again a projection of our input with a linear layer, linear transformation. So we do all this and then we do for multi-head attention, we do them in parallel. We create a list of multiple different heads, as many number as we need, and then we uh, get a concatenation of the outputs from all of these, and then we project it with a linear layer, which is again I think showed here. We do all of these multi-head computations, we concatenate them, we do a linear transformation, and then do a residual connection. So um, yeah, let's so here now we, instead of doing these two separately, we are going to write a function all together. So let me bring in this snippet of code here, and then I'll walk through it quickly. Or instead, just let's write it here. So what all we need to define first is yes. So for this So we have completed the MLP part of it, LN2 part of it. We have completed the LN1 part of it. So all we need is this. So this would be serve dot attention. Serve dot attention come from, I think, here, and here serve dot c10, serve dot c projection. So this would be basically, I'm going to write it first and then talk through it. So these two other layers. So projection layer, I think, is very straightforward. With this block, we have this linear layer which talks about the projection layer. Attention is what is going to be a bit complicated. So we are feeding in vectors of dimensionality and embed. But here, why we are transforming it into con 3 times of an embed is because, as you would have seen, in our head single head computation, that we initialize 3 linear layers for query key and value. So those query key and value, they do matrix multiplication internally. Linear layer is basically a matrix multiplication with input. So here, our just to gain some efficiency, we are, instead of doing 3 matrix multiplication separately, we are clubbing them all together. So this would be something like, uh, let's say, query key value. This would be 3 concatenated matrices, query key value altogether. So therefore, the number of columns in this gets 3 times as much. So that's what happens here. Then we'll need linear layer projection we have defined. Um, cool. Okay, so let's get on with it. So a few more things we'll need is self dot n head, or n head self dot. So basically n head is already in config, or we can call it as config dot n head. This would be config dot n embed divided by config dot n head. So head size is the dimensionality of output coming from each head of that multi-head self-attention, and it would be decided by the number of heads that you want. So this should be exactly divisible, and yeah. So if that is it, then we'll need one more thing, which is self dot a register buffer, which trill kind of buffer, lower triangular matrix kind of a masking parameter, a matrix which would be helping us in the masking part of it. So we will register it as a register buffer so that it doesn't um, it doesn't show up in the parameters of the model. Basically, we name it as bias. Why bias? I'll show you in a bit later. Dodge dot trill, dodge dot once, config dot block size, block size. we will view it as something like 1 by 1 by. Okay, so this is the register buffer that we defined. This is basically a lower triangular matrix with all the ones in the lower triangle, and the upper triangle gets all zeros. And we view it as in this shape because it would be uh, when we'll calculate our attention scores, we'll see that it would be easier to do the masking on top of it, uh, instead of relying so much on broadcasting. So if we also technically, if we leave it out, this line of code, it is still fine, it should work, but it is being done just to uh, rely lesser on the broadcasting of Python. So we have defined all the attributes that we want for this layer, self-attention layer. This attention, now we are going to compute attention. So first we'll propagate the x through C attention. This would give us if attention is if b by t by c, b by t by 3c, we'll get this 3c. So then q, k, v, we can split these 3c into c, 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 three equal segments. Q, k, v dot split config dot n embed size and dimension on along the dimension of -1. So this will get b by t by c dimensions for each. So we'll get query keys and values for each of the tokens of this shape b by t by c after splitting it. Once we have split it, now next we want to so because we are also doing multi-head attention in the same thing, so what we want to do is, suppose for q we want to make this of size b by number of heads by t by head size. So here c would be equals to number of heads times head size. To do this, what we want to do is we'll first let's say we'll have to view this first as b by t by c equals to x dot shape. So we'll first split this b by t by self dot n head and self dot head size. So we first transform this q into of this size from b by t by c to b by t by nh by hs, and then we transpose it to uh, 0 1 2 1 and 2. So this would become b by nh by t by s. So what is going on in here is, or let me, all right, so all these three query key and value projections on those matrices for that particular input, what we are essentially doing is, first we are splitting the b by t by c, which is ideally um, um, which is ideally the output of C is dimensional, is the output of the all the end result of the multi-head attention. So here we are breaking them down into all individual heads for each example in the batch to be T by HS size matrix. So what will happen with this is, when we are going to calculate the attention score, attention would be Q at K dot transpose. So what we are going to do is B by NH by T by HS times B by NH by HS by T. So this will give us result as B by NH by T by T. So you see, this we score for each head in each example, and for each example in the batch, each head would have affinity scores or attention scores of T by T shape. That's what we desire. So it is basically we are transposing these two dimensions T and HS. So it would be minus 1 minus 2, or we can write minus 2 minus 1. And as a product of it, we need to do math dot sqrt dot size minus 1. So this is a scale from, and this comes from the scale dot matrix and scaled dot self attention, scaled self attention. What was the name of that in the attention? Is all you need paper, and quickly look at it. Yeah, scaled dot product attention. So that's the scale part of it. We divide with square root of the size of the dimensional size of the k, and this would give us attention score. So now we have scores of this shape b by nh by t by t. So now here we have to mask each of the uh, t by t matrices that exist in this, so that we don't get we don't the attention module don't look at the future tokens. That's what is we are achieving, striving for. Or let me not write this at 10, let me write this affinity scores dot, I will call masked fill to it, wherein we'll pass in the dot bias. We can call this register buffer with self dot bias, and we'll index into it so whatever number of t's are here. So here this small t I have written in small just because of the not using the extra shift every time, but this is same as capital T. So this t can be anything less than equal to 1024, which is our block size. And whatever the sequence length we have for that particular instance, we are taking this self dot bias equals to 0, where this happens. We'll write minus infinity here. So this will also be b by nh by t by t. So now you see here, if we would have not viewed it in this 1 by t by block size dimension, we could have not indexed it here. We could have just indexed the two dimensions of it, block size by block size, and then we could have used this masked fill. But and that would have used a broadcasting feature, as in it would have added those two dimensions to mask this matrix of four dimension b by nh by t by t. Therefore now affinity scores equals to affinity score, or we'll say soft max dem equals to -1 t by t. So along that last t dimension, we are doing the soft max of it. Before I go ahead with this, let me quickly, what I think is better to do is, if I can elaborate this part. So let's switch to a notebook to do that. Yeah. So let's say we have a QKV dot random of size. This is a b by t by 3c, right? Let's say b is 2, t is 2, and 3c is 3 into 3, 2 by 3 by 4. b by t by c equals to 2 by 3 by 4. b t c. QKV dot split c dimension equals to -1. So now QKV of all rows, and in columns we have till C. Let's print this, and also print, say, Q. This should be same, 0.5625, 5625, 5805, 5805. So ideally what I'm thinking is that these two things should be similar, right? Okay, so before going any further from here, after calculating our affinity scores, I wanted to quickly look at these steps individually, these splits, views, and this masking step at a very granular level, how they are working. So let's say I have a QKV tensor of shape b by t by 3c. So if I split it by each c size along the dimension -1, which is this split, so I'll get three different tensors of shape b by t by c each. So this we can verify by indexing explicitly all the batches, all the time dimensions, and first c elements along it, and we call it q. And we compare if this indexing element and this q are same. So it gives out true. So it means our split is working fine. So it's the same thing that we are um, basically doing here. We are extracting QKV out of the QKV variable. Q's, K's, V's. Then if you see Q's shape is B by T by C, which is 2 by 3 by 4. We wanted it to be of we wanted this Q to split for multiple heads uh, as defined by the config class, config object. So we'll need different Qs for different Qs, Ks, Vs for different heads individually. So we break the C into NH times HS, number of heads by head size. So this becomes B by T by NH by NS. So let's say NH and HS are 2 and 2. Then this is the shape. Now, and we apply on top of the view, if we apply transpose of first and second, so this becomes B by NH by T by HS. So B by NH, which is 2, by T, which is 3, and by HS, which is 2. We want this because for each element in the batch, and in each of that element, for each head we want a t by head size dimensional matrix to calculate our affinity scores, and then matrix multiply with the values to get the final output out of it. So that's what is happening in these lines here. That's why we are applying dot view dot transpose. If we directly try to view this as q dot view by b by, let's say, number of heads by t by head size, so what would happen is it would give an error, which is view size not compatible with input tensor size. It is because due to the sizes of these set in this way that the strides do not satisfy this view that we are asking it for. So that's why we cannot straightforward go ahead and do the view of this exact shape. We have to do some manipulations, tensor gymnastics of viewing it in b by t by nh by hs, and then again transposing the first and second dimension. That's what is going on here. Then affinity scores is pretty straightforward, that we are trying to do QK. So let's say we have viewed all of these QKV. Then we apply calculate our affinity scores this way. I'm not doing the scaling part here. That doesn't count for tensors manipulation. So I've done this. Affinity scores comes out to be B by, I think, NH by T by T. So that's what we are expecting, B by NH by T shape. And so here the register buffer that we did bias name, I'm working it with a trill variable, which is a triangular matrix of 3 by 3 size, which is corresponding to this T by T matrix. This is a lower triangular matrix. This will help us mask the future tokens. So when we do the mask fill and apply the softmax on top of it, it will just become like this. So the in a batch, each head will have this kind of affinity scores. What it tells is for the first instance, for the for the first token, when only one token is the input, it is paying 100% attention to it. When first two tokens are the input, it is paying zero point 0.2 and zero point 0.7 um, uh, attention to it, to first and second token. Then when these are when all three tokens go in as input, these are the affinity scores. Then once we have the affinity scores, we can matrix multiply with this V. So T wedges. Yeah, so this matrix multiply will give us the final output of the attention, self-attention blocks, multi-head self-attention, which will be of the shape B by NH by T by HS. Therefore, here now, once we are done with this, okay, before we, now we can continue here. Okay, so you see first the shape here is B by NH by T by HS, right? That's what shape we get out of this matrix multiply. So we need to bring this, but because from a multi-headed attention output, all the headed outputs are concatenated and then that is projected. So what we need is B by T by C, where C is NH by NHS, HS. So what we need to do is we need to first view it as, first we need to transpose it as 2, um, and after transposing it, it becomes B by T by NH by HS dot view uh, B by T by C. So this would give us B by T by C shape matrix. But there's a catch here. It won't work because we need extra contiguous operation here, because when we have, let's say we have a this tensor of shape this, after transposing it becomes B by T by um, NH by HS. So what's happening here, let's see, is let's say that we have calculated our affinity scores, which are these. So y comes out to be of shape 2 by 2 by 3 by 2, just B by N H by T by HS. So y looks something like this. Yeah. Now, if we directly try to go from this shape to B by T by C, where C is NH time HS, it does something wrong. What we want here is, so this is one batch, this is second batch. In one batch, this is first head, this is second head output, right? For each head, the output is 3 by 3, which is, um, sorry, 3 by 2, which is basically the uh, time dimension by hidden size dimension. So what we want is, for each time in a head, um, we want this tensor which is for first time step from first head to be concatenated with this. But here if you see what is happening is, if we do this operation, instead what it does is it is concatenating this, the hidden size dimension representation of first time step after multi-head attention with 0.1635, which is here with the second time steps representation. So this is a problem that happens if you directly view it in that way. So instead what we have to do is uh, we have to transpose it first, b by t by nh by hs, and then we can view it in that direction. So mm, so even then it doesn't allow. So what we have to do is we have to contiguous operation, then view it. So it should give us the correct thing. Yeah. So now it is um, concatenating this first time steps representation with the. Let's redo these computations. Right. So we are concatenating this HS dimension representation for first time step with this, which is um, uh, first time steps representation from the second head. This is from the first head. Then this is should be concatenated with this 0.1635 with 0 minus 0.3842. Yeah. So this is the correct. And so you see the differences between these two. Um, that's why this is the correct way to go back from this shape b by nh by ts hs t by hs to b by t by c, and once we do this then we can return the y. So this will be the output we will get out of causal self-attention. Alright, going forward, I think now we need to also write a forward for this. um, X equals to self dot layer norm 1 x equals to self dot attention x equals to self dot layer norm 2 x. So here one another thing we need to focus on is doing forward propagation, forward step in the this block. First we go through ln layer norm, then there's a linear layer which is obviously the internally this thing, mm, see attention this layer, need not worry about it. But after the output of this head, so after the output of this attention, we are going to uh, go for a projection. So here I think after the scores that we got, we have not done the projection on top of it. That's one thing pending. Self dot c underscore proj of y. So this will make b by t by c to b by t by c again, because this will be a c by c linear layer. this will transform C-dimensional vectors into different same C-dimensional vectors, but there's a linear projection happening. So we have done that linear projection now, and output will be the this arrow here that we get. So on that arrow, what will happen is we need to add the x before layer norm. So what we can write to it as serve dot attention plus x. So we take a x, this is the residual operation. We take x, we do layer norm, we apply attention, multi-area attention on it, then with it we add the input to it. Now this x will go through another layer norm, then feed forward. So serve dot mlp plus x, and we'll return final this x. So that's it. These are the two operations, residual operations happening here. And I think now our network should give the correct desired these things. Let's say number of layers, I do only two for now, for time being. Yeah. Okay. Conflict of 10 layers. Triple. Okay, I think I missed putting range on this in this for loop. Let's see what happens now. Cool. All right. So maybe and 1 and 2 0. Why is there no attention here? Block. Cool. So now let's compare. I just say 1 for the sake of comparison. Okay, so we have word token embedding, vocab size by an embed, uh, word position embedding, block size by an embed, then layer norm, weight and biases we have of 768 size. Attention bias we have. Okay, so this is the register buffer that we get. Now here you don't see it because these are coming as mask buffers. So to do that, what we can do is persistent equals to false. If we do that, we should stop seeing that buffer basically here, and it won't come in. So yeah, we have removed it. Now you see the attention has C attention weight, C attention bias, C proj weight, C proj bias. Here also it is the same. It is although of transpose shape, 768 by 2304, 2304 by 768. This is 2304, that's okay. 768 by 768. So these are also transposed. So what happens is in TensorFlow, the linear weights show in a different way, which is 230. It shows in a transposed fashion as compared to PyTorch. So we'll have to do a transpose while importing the weights from Hugging Faces model. But these are correct. So from PyTorch's convention, these are correct. Yeah, cool. Then in the end, we have layer norm 2 also. My MLP's projection, uh, CFC, where's the CFC? Sorry, there's something wrong here. Fully connected layer, we have not defined. Sorry, where do I put commas? MLP CFC weight, MLP CFC bias, which are fully connected layer. This is a projection layer weights and biases. So these also would be of different transposed shapes. 768 by 3072, 3072 by 768. Same for this. So we have to take care of all these things while importing the weights from Hugging Faces model. Last layer norm, which comes from this layer norm after all the transformer blocks are completed. Then a linear, which is basically LM head. Then this will give us the logits. So yeah, we are ready with now. Just if we update this with 12 number of layers, this should give us the exact same number of layers as this. So 0 till H11, then we have LNF weight, LNF bias, LNF weight, LNF bias, then LM head weight. Cool. Alright, so now we have completed the skeleton class that matches the state dictionaries from Hugging Faces GPT-2 model. Now next is how do we take the weights from this model, the actual tensors, and port it or import it into the tensors that are initialized by this model. So this is just an initial random initialized model. We want to get the trained weights into it. So we want the weights from Hugging Faces model to be in this our custom written model, and then we'll use it to infer. So first let's start with writing a method for loading the weights. So we'll call it as from pre-trained. I'm going to make this method a class method because we can directly call this method on this class. Before we do that, so we need to assert that model type is in one of these GPT2 or GPT2 medium or GPT2 large or GPT2 XL. So only these one of these four models can be used with this method of this class from pre-trained method. Once that is all right, we can start with config. So to get this model defined, we'll need some configurations, right? These configs basically. So we'll start with config args equals to A dictionary. Where we'll say, or we'll do something like dict of and layer equals to 12. GPT-2 would be a dict of mm, what things change with the model. Vocab size remains same, block size remains same. Only these three things change. So we'll say m numbered equals to 768 and layer equals to 12 and head equals to 12. Similarly, we'll do it for all these models, large. Okay, so I've updated these hyperparams for these. We'll also need a few more config uh, arguments here, which is gap size, which is 50,257, and config args 1024. Once we have our config args ready, we can now do two things basically. So we'll import lm head model and model hugging face equals to 52 from pre-trained. We'll say model type. So we have our model loaded, hugging face model. Now our model is GPT-2 config args passed to it. Sorry, my bad. Config will be GPT config args passed to it config. Now we have these two models imported and made. So state dict for model is model dot state dict. State dict for hugging face model is model hugging face dot state dict. Now we have both state dict defined. Um, Now here we have made these as persistent equal to false, so they will not show up in the state dicts. Therefore, we can leave out some pre-processing or filtering from this state dict. Otherwise, sorry, this one our custom one. Otherwise, we would have to remove the keys with those state decks where these are showing up. We'll have to ignore those specifically, but right now we don't have to do that. Therefore, attention.bias keys. Keys for this is sd dot keys hugging face equals to both keys. So the layer names we have extracted out of these two straight diffs. Now what we want to do is um, one thing to note is I remember for these particular weights, these layers, I told that the weights that are shown here are of transposed shape as compared to what it shows in our model. So we'll have to make a list of all these layers which will need to be transposed before importing the weights. So we can say that transposed equals to, now the thing is that I remember these, otherwise you would ideally compare the two models weights side by side and then do them. See projection also. Then we would need CFC dot weight. Mm, let's say, let's write this as well. MLP dot CFC dot weight, and also MLP dot cproj dot weight. Cool. So we do one more assertion, length of SD keys equals to len of SD keys of Hugging Face. Otherwise, we'll say, otherwise we can say here that keys mismatched this not equals to this. If we pass this, means both the keys are same, the keys in both these lists are same, then what we can do is for k in SD keys, if k dot ends with w for w in transposed, if uh, any of these string matches with ends with is ending in the k, if k is ending with any of these, then what happens is we assert first that length of k dot, sorry, sd k dot shape Rather, let's say this way, hugging face is equals to k. If the transposed, this gives the shape, and this indexing will give the transpose of the shape that you are looking at. So basically, transpose of hugging faces shape of this particular key is equal to the shape of our key, and only then we say sd k dot copy sd hf k dot t. Else we need not do this, but we need to shape equals to this dot shape, yeah, but we'll copy it as is. Also we can do one thing is, so we copy do this copy operation without any gradient calculation indication. So then uh, once this is done, we would have, so here depending upon if you have some extra buffers or any more keys happening in your model, in your custom model, then you would have to ignore those keys. But right now we don't have these because these buffers have been set to persistent equals to false, so they will not show up in the straight dict keys. Therefore this model should load, I think. So now let's say, mm, if this basically runs through, means this function will go through, that means we'll, alright, also we should return model here. So this way should give us the model. If this runs through, means we have loaded the weights successfully. Let's see. Cool. Looks like then we are able to load the weights successfully. So next step would be to just try to infer these, use these loaded weights to infer by giving in a prompt and see the generations and then compare those generations to the ones happening from Hugging Faces model. So now we want to we have loaded this model from pre-trained weights from the Hugging Faces model. So next step is to do the generations using this model. To do that, we'll need to write the forward pass for our GPT2 class, which we have not written yet. For all the individual components in the class, the forward pass has been written. But for this, we need to write for GPT2. So let's start with it. Uh, So B would be X given would be of size B by T, where B is the batches and T is the time steps for each of the element in the batch. we need to make sure that t is less than equal to config dot, let's say, self dot config dot block size. So when we do this, first step after we ensure that t is less than block size, next step is to calculate the position embedding and the word embedding. So for position embeddings, we'll need positions for these sizes. Toss dot arrange 0 till t. D type is toss dot long, and we'll need to move this on x dot shape. Sorry, x dot device. Then pose embeddings equals to self dot transformer dot WPE, and we pass on the positions here. Token embedding equals to self dot transformer dot WTE, and we pass on x to it. So this will give us b by t by an embed. This will give us b by t by embed vectors. Therefore x equals to position embedding plus token embedding. Now this tree for block and self dot. Now we need to iterate through all of the transformer blocks in the model, and then pass it through x equals to block of x. So after out of this we'll get b t by c or n embed size of x. Now after these are done, then last we need to perform the layer norm. Out equals to self dot lm head self dot lnf of x. So this would give us b by t by vocab size of embeddings, or rather say these are the logits. So just be mindful that right now we are not calculating losses here. We are not applying dropouts at many positions that we should, because we are just trying to um infer with the pre-trained weights, and that doesn't change the structure of the model to load the weights and infer from it, those kind of things. So we are not doing those yet. So sorry, my bad. Transformer.lnf, because this is the part of transformer module dict. So this gives us the logits. Now forward pass is kind of complete. Now we can go ahead and use this for generation. Encoder is tick token dot get encodings GPT2. Prompt equals to I am a language model. Put IDs is encode prompt we need a few parameters here. Number of return, max number of tokens equals to, let's say, 30. Mm, equals to, let's say, we do this 30 x. How many sequences we want to return? That we do it as 5. Input id equals to put ids toss dot tensor of input ids d type equals to toss dot long, and we also want to, so right now this is of shape whatever, shape is like t, length of t, right? This is also of shape of length t. We want to make this of shape, so here we want input IDs of shape b by t. So what we do here is IDs dot, we unsqueeze a dimension along 0, and so this will make us 1 by t shape. So it will be add on a dimension along 0th in 0th dimension 1, and then it will have to repeat it by number of return sequences, comma number of return sequences, comma 1. So this will make us b by t. Print input IDs dot shape. Let's see what it does. Okay, 5 by 8. So 8 is basically the tokenized version of length of tokens coming out of that prompt, and 5 times is what we are repeating it. So yeah, this is correct. Now what we can do is, once we have this, we can go ahead and make access torch dot, or not needed, everything is on same device, whatever it is. Then let's work on the generation. So here x is of shape 5 by 8, right? So we'll start with the loop while x dot size first dimension X is of shape 5 by 8 right now. We need to keep generating here till this gets to 30. So this is less than max length with close dot no grad. Again, so we need to put a model in the eval mode. Now let's do a forward pass. Logits equals to model X. So this we'll get as B by T by vocab size. Now we need to predict B by T by B by 1 B by 1, basically new token for each of these, right? So probabilities equals to f dot soft max logits, and we need to take the last time dimension, so all the element in batches -1, all the vocab size along dimension equals to -1. So this would become a B by vocab size, B by vocab size tensor of probabilities. For each element in the batch we get a probability of size, vocab size. Then mm, so here we want to use top K and top P basically. So how the Hugging Face does is top K. So top K as in filter out the top K probabilities. If K is 10, then top 10 probability elements from the probs tensor, and then from there we will just have to basically sample out of those top 10 probabilities. So we'll say top K probs, top K indices equals to top K probs, and let's say top K is 50, dimension equals to -1. So we'll get here is top K probs is of shape B by 50, indices is also of shape. For each of element in the batch we get a 50 top probabilities or indices of those 50 top probabilities. So now what happens is we get index equals to toss dot multinomial top K probabilities, sample 1 for each, we'll sample only one element for each. So this will give us B by 1 for each element. It will sample one probability IDs, but here what will happen is the IDs that it will return is corresponding to the list of probabilities that we get here for each element in the batch. But those probabilities have again been filtered from this probs. So we need correct indices that correspond to this probabilities to get the indexes corresponding to those tokens. So we get x col equals to torch dot gather. We'll have to do top K indices and -1 ix. So from top k indices, which is b by 50, along the minus last dimension, we pick out the IDs there corresponding to these. So if this is 2, the second ID that exists in this vector of 50 length, we'll pick it out. So this will become our x call, which would be of shape b by 1, x equals to torch dot cat x x call dimension equals to -1, or rather you can say here is 1. This will make it as b by t plus 1, b by t plus 1. So next time our size t plus 1 will keep growing until it grows to maximum length, which is 30, and at that moment it will stop. Now we have the all the generations out of this, means all the token predictions, 30 token predictions including the original length. So now we'll have to decode and print text for I in the sequences. Tokens equals to x of I. So we take each element in the batch, convert into the list, and then we just will have to decode these using the decode function in the encoder. So decoded equals to enc.decode tokens, and then we can print decoded. So this would just print our text these many number of times. Cool. So yeah, we can take it for a spin. Let's see if this works. Let's save this. Or it gives some error. Hope not. Okay, there's some problem going on in here. Hmm. I think there is a problem here with MLP. Okay, yeah. So I'm not returning this X. That's why it's. Okay, weights loaded. Cool. I'm getting the generation as a way to say it's generating 1, 2, 3, 4, 5. 5 generations, a language model of the world. I think it's interesting. So you know that I mean. And I was going to write a nice thing for Python. So yeah, it looks good. We are able to generate. I don't have it handy, but using the Hugging Faces GPT-2 model, when I was doing the generation, giving the same prompt, I was getting kind of similar results, not exactly same, but I think yeah, we are on the right track. So This is it for the first part, wherein we wrote a skeleton class for the GW GPT2. We loaded the pre-trained weights from Hugging Face's GPT2, and also wrote forward pass so that we can infer using those pre-trained weights. And um, yeah, I think that's a good point to close this video. Then we'll further continue along tomorrow onwards how do we train our own GPT-2. Thank you. Have a good day. Bye.